Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover Newton's method for finding roots. And we're going to start out with the linear approximation method for finding f of x, near a value where x is equal to a. So we're really saying that, the function value can be approximated by the tangent line near some, a value. So if I have some, say, a value right here, we know that the tangent line is equal to this thing. So that means the value of the tangent line would be equal, would at least be close to the value of the blue function near, that x equals a. So again, if I pick a point really close to it, right here, map it up to the blue function or map it up to the tangent line is going to give me, y values that are very, very similar. So what I want to do is I want to estimate some roots of this blue function, and roots of the blue function end up being these pieces right here. We're talking about their zeros or their roots. So the way I'm going to do that is I want to try to estimate values for which both of these things are equal to 0, where the tangent line is equal to 0 and also where the blue f of x is equal to 0. So instead of just where f of x, I need this to be equal to 0. Now I'm writing x sub n as opposed to a because what we're going to do is we're going to iterate this method. So I'm going to get better and better approximations for the 0. All right, so this is how it works. Say this right here is x sub naught. Instead of calling it a, we'll call it x sub naught. And what I know is that the values of x sub naught are very similar to the outputs of x sub naught are similar to the blue function as it would be to this to this tangent line. That being the tangent line, the thing I just drew, and the blue function being this piece. Okay, so now what I'm saying is that since these two functions are very similar, they're going to be, 0 at very close spots. Well, very close, but kind of close spots. So I can see that the 0, the blue of the blue function is this pink, and the blue 0 of the tangent line ends up being this. Now this thing ends up being our x sub 1 now. So the very first thing is I plugged in, say f sub 0, so f sub 0 plus f prime of x sub 0 all over x minus x sub 0. And I really just tried to figure out, where this thing was equal to x. So, this x sub 1 really is the solution of this particular point here, because I'm saying when this thing is equal to 0. So what I'm going to do is I'm going to go ahead and solve this thing for this x value, which ends up being this piece here. So in order to do that, I'm going to subtract off this f of x sub naught is equal to f prime of x sub naught times x minus x sub naught. And then we're going to divide this over, so then minus f over x sub naught all over f prime of x sub naught is equal to x minus x sub naught. And last thing I'm going to do is I'm going to add x naught to both sides. So then I have x naught is equal, x naught minus this f of x sub naught all over f prime of x sub naught. And of course this is equal to our x. So in this case, this is going to be equal to our x1. I know I labeled this x, but it's really that x value right there. So what I'm going to say is when I plug in x naught, x starting at 0, what I'm actually going to get is I'm getting a new value of x. So let's call this the next value. So if the first one's going to be 0, the next one's going to be 1. So we'll call this x sub 1. So I have a general equation. If I was able to solve, this first equation for x, instead of, these things saying naught, they're going to say x sub n. So then what we can say is x sub n plus 1 is just going to be equal to, this equation here, except instead of the naughts, it's going to be x sub n. So this is going to be x sub n minus f of x sub n all over f prime of x sub n. So again, this is our x1. Now what happens is I can tell that these values are relatively close to each other, kind of close, but I can do better. So what I can do is I can do an x2. So what I know is if x1 is equal to this thing, if I plug this x1 back into this formula again, what's going to happen is this is now going to plot down, and I'm going to be able to figure out a new tangent line to this particular function, and that tangent line is going to look like this, which means that the 0 of this new tangent line is going to be still pretty close to the 0 of the blue function of our f of x, but notice that it got a little bit better. So this value we're going to consider our x sub 2. It's our next x value. And then we're gonna do it again. I'm gonna plug x sub 2 into here, and this is gonna give me an x sub 3. And what that's gonna do is it's gonna plot it back up to the function, and then it's gonna give me a new tangent line, and that's gonna come across. And we can see that we're gonna get even closer. So the idea is if we iterate this over and over and over again, what's gonna happen is it's gonna bounce back and forth until it really kind of converges to that pink 0, the true 0 of this blue f of x. It will, the converge means it's really, really, really close. So you get to choose how accurate you want. You're like, how many decimal places do I need? Well, I just, I can keep taking it out until, my calculator quits changing, and you just get the same number over and over and over again. You can see that's really kind of the convergence to your 10 decimal places that your calculator usually gives you. Okay, so this would be x sub 3, and then so on. Okay. All right, so let's put this into practice. So what we're going to do is this is our formula here, which honestly is just us taking advantage of this linear approximation formula to be able to iterate to find zeros. Now, things that we have to be careful of. Sometimes you might pick an x naught value, and you might approach a different zero. So for instance, if I didn't pick this x naught that was relatively close to this 0 by it, say if I picked, I'll have to erase some of this. Say if I picked up here instead. What if I go with this value here? This value. You can notice if I plot that thing up, what's going to happen is this tangent line is going to look like this. And if this function doesn't, if it doesn't converge, this thing completely misses the x-axis here. And, if this function continues, maybe goes up forever and ever and ever like that, we notice that this will never really, when I hit the x-axis, it's still not going to get back to this particular point. So the one true problem with Newton's method is you need to pick an x value that's relatively close to your 0. Relatively close. So it really kind of has to be almost within this kind of this area here, or this this interval here. So you have to be wise with your choice of x naught. If not, it might not converge. But if it does converge, it will converge to a root of the function. So another problem is, what happens if I pick a number right here? What's going to happen is this is going to go way across to this. And then when this plots up, what's going to happen is as you iterate, you're actually going to find that 0 instead. So again, you still have to be relatively close to this particular 0, or you might find a different root that you're not actually looking for. But again, what it does say, if Newton's method converges, it will converge to a 0 of the function. All right, let's put it to practice. So here's our example. F of x is equal to 3x squared plus 13x minus 10, and I'm going to give us a choice for x naught, which is equal to 0.5, which is really kind of the first things they do in calculus. They give you this value. Other times we have to kind of choose it ourselves, and you can use a graph. There's a bunch of ways to kind of choose this. Okay, so in order to do this, what I'm going to do is I'm going to figure out what f prime of x is. I need to plug it into here. So f prime of x is equal to 6x plus 13, which means now this formula here, our x to the n plus 1, is equal to x to the n plus f, so not plus but minus f of x to the n. For some reason, a lot of people mess up that minus sign as well. So this is going to be 3x to the n squared plus 13x to the n minus 10. And then this is all going to be over 6x to the n plus 13. All right, so what I'm going to do is I'm just going to use a calculator. Everywhere there's an x to the n, I'm just going to type in x. So I have, x minus, be careful with parentheses. If you use a calculator, you're going to want to do this, okay? So minus, we have 3x squared plus 13x minus 10, and then divided by 6x plus 13. Okay. when I hit enter, now it's into my calculator. Now what I have to do is I have to pick a choice for x. So what I'm going to do is I'm going to go 0.5 and I'm going to hit the store button. The store is that STO with a little arrow. It looks like this, STO with a little like little arrow here. I'm going to store, so I go 0.5, hit that store button, and then I hit the x button, you know, the x and theta k, xt theta n. So 0.5, store to x, enter. So now 0.5 is going to be that x, or in really case, this x to the n. So what I'm doing is I'm plugging in, you know, 0.5 into here. So 0.5 minus, you know, 3 times 0.5 squared plus 13 times 0.5 minus 10, all over, you know, 6 times 0.5 plus 13. So this is going to give us, remember that I'm putting right now x0 in here, so this is going to be our x1. It's going to be our next number. So I'm going to go up and grab that equation since it's stored to x. This gives me 0.671875. Now if I want to find x2, what I do is I plug this number back into, you know, all the x values. So instead of having 0.5 here, I have this number in here. So 0.671875 minus 3 times that number squared plus 13 times that number, 0.671875 minus 10 all over 6 times 0.671875 plus 13. And so the way I do that is I have this new number in my calculator that says that 0.6715. I just hit the store button, hit x again. Now that thing's my new x button. I go back up, type in the equation that I had before, and then hit enter. And this gives us 0.6667145. Now I'm not going to write this all again, but this number goes back in those next spots. So if I do an x sub 3, you know, again, this number is going into all those locations again, or it's going into all these spots here. It's going into, you know, I'm plugging it into this spot over and over again. So I will store that new number to x, enter, and then go up, grab that equation, hit enter again. So now the next gives me x3 is 0.66666666667. And, you know, if I store that to x, go up and plug that into the equation and do it again, what I get is I get exactly the same number. So it now converged after that particular, well, converged, you know, numerically on your calculator. And it looks like this is going to be equal to the number 2/3. Now, let's just kind of verify that this is a 0, and that'll be it for this. So if I have, you know, 3x squared plus 13x minus 10, what I know is this thing I will factor into a 3x, and then this is going to be an x. Now, in order for me to get negative 10, you know, it could be a 1 and a 5, sorry, 1 and a 10, a 2 and a 5. It just so happens to be a minus 2 and then a plus 5 here. So this thing actually factors into this. Now, what we actually found was, you know, it's either 3x minus 2 is equal to 0, or we have x plus 5 is equal to 0. So, you know, x is equal to 2/3, which is equal to the thing that we found, or x is equal to negative 5. So what we could do also, if we wanted to figure out, like, say, another 0, I could, instead of using 0.5, what I did is I chose a value that was close to this particular root, so that's why it converged to that root. If you wanted that negative 5, maybe you'd choose maybe your starting point to be at like negative 6 or negative 7 or something like that, and then iterate it. And what you'll do is it likely will converge to this number, you know, assuming you picked a number that was close enough. But that is the basis of Newton's method. So if you like the content, please subscribe.